Okay. Welcome. Second day, second seminar block, starting with Jens from Individual Computers with his FPGA Commodore 1 seminar. Have fun, give it a hand.
Too early, you didn't see the performance yet. Okay, the reason why we're here is I want to tell you a little bit about the Commodore 1, C1, that's how we call it now. First of all, forget everything you've known about computers. You probably know computers with the CPU, with the graphics card, memory, and everything. The C1 doesn't need a CPU. I mean, you see it running here. You see the CPU card, and it still continues to run. I'll take it out. The FPGAs implement everything.
We have to.
The FPGAs implement everything, including the CPU, the graphics card, and everything. The C1 has two FPGAs. Maybe we'll start with the terms first. The acronym FPGA stands for Field Programmable Gate Array. That means that the chip does not have any dedicated function, but it is programmable in its behavior. It can be anything, like a CPU, a graphics card, or a memory controller, and that's what people have always been doing with FPGAs. They have used them as application-specific chips, mainly for low volume production runs, and the special thing that we're doing with the C1 and that I'm also doing with the Capital MK4 is the FPGAs can be used in a very special way. You have to know that they are programmable, but unlike other programmable logic chips, they lose their contents if you switch to the power up. That means they're very dead and power up, and you have to load them with their behavior every time you power up. The reason why you probably won't notice that these chips lose their contents is that most hardware products that use FPGAs, they have a little loading scheme, a little PROM or whatever that loads the FPGAs once on power up, and then these PROMs are idle for the rest of the power cycle. And the special thing that we introduced with the C1 and also with the Capital MK4 is that the FPGAs stay unconfigured until the user selects a core. A core is the thing that you load into the FPGA, and this behavior can be loaded from a mass storage device on the C1, and that means you have a computer that starts up pretty much with the question, what do you want me to be today? And what you see here on the screen, that is the early startup procedure of the C1. The early startup implements a little RISC processor that does 6502 emulation and Z80 emulation at the same time. So what you see here is mainly Z80 code. It is based on a Schneider CPC, and this Z80 that is currently emulated is emulated in a very interesting way, because the early startup procedure, as you see right here, is that has been developed way before the early startup core has been developed, and that was in 6502 assembly. So this existing code and the new core had to be joined somehow, and that's what Tobias Buchner has done. He has extended his Z80 emulation to also emulate 6502 code. So basically what we got here is the Z80 processor that can run 6502 subroutines. And that's how we got the 6502 code running. Anyone of you have ever seen the C1 booting? Nobody? Okay. This is how it starts as Commodore 64. And what you see here is just an NTSC, 1 megahertz. It's nothing special. It doesn't have any extended sprites or the monster sync or whatever you might have read on the internet. This is not what it's about. The reconfigurability of the computer is much more than just make it a Commodore 64. Unfortunately, I haven't really prepared the FPGA part of it, so we have to do a little bit like questions and answers. Did I see a question there? Okay. Yeah, can I continue? Great, thanks. The FPGA stuff means that this computer can be reconfigured on the fly. Reconfigured means we can change its hardware behavior, and it's a quite interesting new concept of computers. Like I said, you don't have a CPU anymore. You don't have a graphics card anymore. You can always think of extending the capabilities of one part by cutting down the capabilities of the other part. It means if you don't need a large CPU right now, you only need to keep it running. That you can use chip resources for 3D graphics, for example, or the other way around. If you don't need any graphics, but you want to implement something along number crunching like. It can all be done on the fly. That means you can reconfigure the FPGAs to implement new functions without having to switch the computer off. And there is the second trick of the C1. It is 2 FPGAs. Both of them have their own memory stuff. One of them has a big SD-RAM, the other one has normal VRAM. The type of memory doesn't really matter because you don't need very much memory to configure the FPGAs. The bigger one takes about 160K of data, the smaller one about 60 kilobytes of data. And reconfiguring always means shutting them down completely and getting them up again. That means you can't reconfigure partly. So if your product only has one FPGA, then it's really brain dead. It doesn't work. So you have to have some circuits that are around it to bring it to life first. And the C1 approach is to have 2 FPGAs that can bring each other to life. That means the smaller FPGA that runs the early startup procedure that you've seen before, the one with the screen and the yellow characters, that purely runs on the 1K30 FPGA, on the small FPGA, and this configuration procedure is basically loading up a core into the 1K100 FPGA. That is the big one. 1K100 is the type number of this chip. And the trick now is after the 1K100 is started, it can erase and reconfigure the smaller one. So it is kind of a chicken and egg problem, because if the FPGA of your main product is not configured, it can't do anything. But if it can't do anything, you can reconfigure it as well. And yeah, we've just cut this circle open by given the possibility of erasing and reconfiguring these FPGAs back and forth. I hope this is not too complicated. I mean, I see lots of question marks. No? Okay. So, yeah, the trick behind it is to get the memory contents, for example. What you see here, this Commodore 64 core runs the normal C64 software, but the kernel ROMs and the basic ROMs and everything, this is not part of the core. It is only it's real memory contents. Like I said, these FPGAs are also memory controllers in this case, and you can really think of it as the system memory that you can load up, even with the early startup procedure. Unfortunately, I can't show you the directory structure of the early startup CF part. Because the interesting thing is you can exchange the ROMs of the C64 by just replacing the file. Maybe you remember if you wanted to replace a kernel ROM or the basic ROM of the Commodore 64, it was always like soul rate. And on the C1, it's just a matter of replacing a file on a compact flash card. And this compact flash card is even FAT formatted, can be any FAT, FAT12, FAT16, FAT32, it's all implemented. So you can use any size, formatted with almost any operating system. Windows has got a little bit of a problem there, because the identification of CF cards, especially the FAT file system, is not always correct on Windows. Funny, because FAT is a Microsoft invention, and they're the only ones who don't implement it properly. But hey, Linux, the Linux people have found a good solution for it, and we've implemented about the same. So the C1 recognizes even those cards formatted by operating systems that are by design. You can let me go back to the memory controller thing. The FPGAs are of course loaded with their contents with these 160K for the big FPGA, but a Commodore 64 without a ROM wouldn't start. So the idea behind it is that we have implemented a way to load the memory of the bigger FPGA first, before we configure the other FPGA. That's why we have implemented this so-called support core. So when the early startup is running, then a very minimal core is loaded into the 1K100, and this core is only good for transporting the contents of the ROMs into the RAM chip that is connected to the bigger FPGA. So you start up, you move the C1 itself moves the ROM files into the memory, and that is where they stay, where it stays, while the bigger FPGA is erased and then loaded up with the Commodore 64 core. So first of all, we prepare the memory, then load up the C64 core, and then give control to the Commodore 64 core. The 1K30, the smaller FPGA, is completely idle in this case. You see here in the background. This Commodore 64 runs purely in the 1K100, in the bigger FPGA. And we have other cores like the Schneider CPC cores. Maybe we should also show these. They're a bit more interesting if it comes to spreading the tasks between the two FPGAs. I have to power it out first. Loading the support core, that is the thing that I was talking about. These are the shiny things. It's exactly what I was talking about with the feed always takes a while. This core is fairly interesting because it spreads the tasks over the two FPGAs. Like I said, the introduction, the early startup is based on Schneider CPC, and the Schneider CPC uses Z80 emulation. It's not a real Z80 processor, but it's an emulation. Otherwise, you wouldn't fit it into the small FPGA. It's not cycle accurate, but it's about the speed of a real Z80 at 4 megahertz. And the Schneider also had a special sound chip, this AY8910, I think that was the number, very popular chip back then in arcade machines. And this chip is also implemented in this core, but it didn't really fit into the smaller FPGA. Here comes the scheme that we've invented for communication between these two FPGAs. They are connected with a high-speed 8-bit wide bus, and through this bus, what, you're laughing? It is high speed. It's a little bit over 100 megahertz. So. Pardon? Okay. Yeah, the communication between the two FPGAs runs at slightly above 100 megahertz, and that means we can transport a lot of data. The C64 core that we're seeing, it even transports the whole VGA display through that port. It doesn't even scan double. On the other side, it scan doubles already in the 1K100, the bigger FPGA, and that transports the whole VGA picture through this bus. And the same bus is of course used in other cores that spread the tasks over two FPGAs. And this one basically runs in the small FPGA, but the sound generation did not fit into the smaller one. So the sound chip is placed into the bigger one, into the 100 FPGA, and sound generation takes up maybe 20-25% of the 1K100 FPGA. So it would have pretty much filled the 1K30. Yeah, that's how you can spread the tasks between the two chips. So. Any more questions? I would have loved to show you the Big 20 core because since about, I don't know, a few days we have a Big 20 core, but I don't have it on this compact flash card. Maybe I should have prepared myself a little bit better. Question? Great. This joystick, the DTV, is developed by Jerry Ellsberg. She has developed it while... no, this joystick is not an FPGA, it's an ASIC. It's really silicon that is not reconfigurable, nothing at all. So everything I'm talking about here is about reconfigurable computers, about new features that you can add by just downloading something. This does not apply to the DTV. This direct-to-TV joystick, that is really just a gaming thing. So if you got a Commodore 64 at home, then this joystick won't give you anything new. But if you want to have a new computer, a new style of computer, one without a graphics card, one without a processor, that still runs, then the C1 is your thing. C1 runs the Commodore 64 core, but it can be much more. Like I said before, and of course, like you see here, I mean, I'm not a Schneider or Amstrad freak, so I can't really demonstrate this Schneider core, but you can do so much more with it. The DTV is exactly 1 megahertz, and the C1 has a 65816 processor that you can clock up to 20 megahertz, so you've got something like a super CPU with it. We haven't implemented it in course yet, but it's going to be just an internet download for you, and then you basically have a new machine. Pardon? On the C64. You have a floppy drive with it? Lots of them. Yeah, it's an NTSC port. So if you have NTSC software, you have everything. Oh, I don't know how much time we have. I think it's something like 45 minutes. So I mean, if it takes like 5 minutes for you to bring up the drive, and you don't have it. Oh, okay. Unfortunately, no. I would love to show you something, but like I said, I'm not really well prepared, so we got to do a little freestyle. Next question? There is already a lot of documentation about the C1. We have the schematics online. That is probably the most important thing if you want to make your own core. We have a tutorial online that gives you an introduction of how to use the development tools from the FPGAs. You might have heard about FPGAs before, maybe at university or whatever, and you've been using expensive tools there. Most probably these tools are in the range of 20 to 50,000 euros, and that was always one of the biggest hurdles to take before you can start your own FPGAs. The good thing about the FPGAs we are using here is that the development tools are free. You can just go to the chipmaker's website. The chipmaker is Altera. You just go to altera.com and you can download this Cordis development studio. Cordis web edition, I think, is the exact name for it. You still have to register, but you don't have to pay. So you can really start designing your own FPGAs. You can completely simulate them, and the simulation of these FPGAs is pretty precise, which is unusual for design for development environments like that. I've made really bad experience with other simulation tools, but the Altera tools are so precise. It's really amazing. They really seem to know what they do. And the thing is, the next thing you might want to have is you don't really want to start from scratch, because I mean, one of the FPGAs is already running, and on the other side, if you want to make your own core into the bigger FPGA, you still have to talk to the smaller one. Otherwise, you can't bring a picture over. Otherwise, you can't use the sound and everything. So we are giving free cores and source codes and everything to implement existing cores, to make porting cores easier, and to give you a possibility to have a jump start. There is a tutorial online on the C1 website. The C1 website can be reached either through commodore1.com or the website that it's pointing to is c64upgrade.de/C1. And probably the easiest link is to go to my website, ami.ga, and then click on the C1 link. That's the shortest way. On that website, I have this tutorial. It's been published, I think it was mid-December, and since then, other people have started developing their own cores. There's one guy who's making a TRS-80 another one who's been talking about making a ZX81 core. And Tobias Lubner has just ported the 20 core. It's been finished, I think it was last week. Like I said, I didn't have the time to try it yet. And yeah, with these tools, and with all the open documentation that you've asked about, it is your perfect tool to get started with FPGA development. So, to sum it up, all documentation is available. It's a completely open system. Anyone else? Yeah? The question was, what's the CPU part about? We only need the FPGAs. That's right. I was talking about a computer without a CPU before, and that's what it was about in the beginning. We really wanted to implement the computer completely on an FPGA. But if you want to implement a CPU, you are using up a lot of chip resources, and if the CPU is something known, if you don't want to change anything in the CPU, then you are of course free to use something that already exists. And this is the 65816. The CPU part has two things. It is not only the CPU part, it's also a memory part. So it has 128K high-speed SRAM on it. This is really high speed. It's 12 nanoseconds. It's something that it would be a waste of resources if you would implement the 65816 processor on the FPGA. So we much rather like to use the resources for something else. But like I was showing before, the other startup even runs completely without. So this card is necessary for the CC4 core. And it is also used by the Turbo CPC core. That's another one that I haven't talked about yet. It's, well, we call it more like a design study of a Canada CPC with a cycle exact but very fast clocked C80 processor. And, yeah, this is something that we really didn't think about before, but the reconfigurability gives us this possibility to implement completely new machines that haven't been built before. Because, I think none of you has ever seen an accelerator part for Canada CPC. Okay. There was another question? The question is, how do you reconfigure the FPGAs on the fly? Of course, your cores have to be prepared for that. So the Commodore 64 core, as you've seen it, and of course the Schneider core that's currently running, they are not prepared to reconfigure the small ones. So they expect the small FPGA, the 1K30 FPGA, to be what it is when it's starting up. So this VGA multiplexer, this communication protocol between the FPGAs, that is all set in this behavior of the 1K30. So if you really want to reconfigure, then the designer has to prepare his design for reconfiguring the other FPGA. I guess the first point to show reconfiguring one FPGA with the other, that is the Turbo CPC port. I said that earlier. Any second question? The question was, is it a software or a hardware problem that the Schneider CPC is not cycle exact? It is actually quite hard to answer because I have a hard time saying that a core, an FPGA core, is software because it is so close to the hardware. I mean, it is still something that can transport through the internet, so you might want to call it software. The reason why it's not cycle exact is that it is not real Z80 processors running in there, but it is a very cut down RISC CPU that's running, and this RISC CPU is emulating the C80. So actually, what you're seeing here is a CPU emulator surrounded by real hardware, and this whole combination gives you a computer that acts pretty much like an Amstrad CPC. But since the CPU is only an emulation, and it's not a very exact emulation, well, you might want to call it broken by design if your aim would be cycle exactness. But it wasn't. The target was to get this thing running first, and maybe have something cycle exact later. And since there are free cores on the internet, you can take a Z84 and compile it on the C1 with all the free documentation that we're giving. You can make it cycle exact. This Turbo CPC board, it came out when Tobias Hübner started to call the Z84. It was cycle exact Z84. And he did that when he got it running first. He thought, well, it's so much resources that are in there, and so much power that's in there, because this is running on an FPGA that can be clocked with up to 100 megahertz. And you are only running a Z80 processor at 4 megahertz. That's not fun. That's why he started working on a Turbo CPC core. So this Turbo CPC core can be cut down. It can be cut down to 4 megahertz. And then we really have a cycle exact CPC, a cycle exact Z80 processor. So it's already been done. So we really don't want to reinvent the wheel. The trick was to make it all fit into the small FPGA to make the machine running. It's this chicken and egg problem that I've been talking at the beginning. The FPGAs are brain dead at the beginning. You need something. You need a ROM or a flash ROM or whatever to boot it up from. That's of course what we have on the C1. It's a 512K flash chip that we're using there. But of course, it's got limited resources. You can't just put all the ROMs and all the cores on them. So what we're doing is we're putting a loader on them. So you switch it on, you're presented with this menu, and what you're seeing there is already a core. But this core is asking you what core do you want to load. So it's a little bit weird. But it's, like I said, new style of computer. You just have to get used to these new ideas. Any other questions? Let me answer the first question. The question was how complete is the C64 core? How many features are missing, and what is It's first of all it's an NTSC core. That means you can run any PAL demos unless you want to see it just flickering. And this core implements the CPU. The CPU is cycle exact. And the cycle exact CPU has a few extensions. It has some extra opcodes, and these extra opcodes are also documented. Not yet quantitative, but we'll do it. The opcodes are not very powerful. It's mostly the things that back certain registers that are not memory meant for the C64. The video chip itself and the CIA chips and everything, that is pretty much cycle exact. The video chip is, you can really do SLI effects, you can do Wesker effects, and you can do spline multiplexing and everything. It is a Commodore 64. It feels like a Commodore 64, programmed like one, and it's a new C64. And I guess for the second question, that was for the native mode when it's going to come out. To be honest, I can't tell because this other question is for DTV. It is related because this woman who initially started the C1, Jerry Ellsworth, she didn't really abandon the C1, but she doesn't put very much time into it. So we have to hope that she'll make this native call one day. Otherwise, well, we'll do it. Tobias and I will do it. This question was how far is the native code completed? The source codes are all there. I have this other one there that has been demonstrated in 2001 and 2002. That worked with the 80 characters display with the huge sprites and everything. That thing works, and that has also been developed on Altera FPGAs using the same development software, this core development software. So it is not a matter of redeveloping it from scratch, but just porting it from the prototype board to the mass production. And I'm just hoping that Jerry will put some time into it. The C1 is currently only sold as an FPGA development board, as something that is in beta. If you are interested in developing your own cores, then this computer is for you. But if you are mainly interested in a C64 on steroids, then you might want to hold off buying it. Anyone else? Yeah, wait for the microphone and I don't have to. So
what piece of hardware is the CPU for? The red one. Yeah.
It is. No. It's a real CPU. It's a 65816 CPU. You can switch it on. You can take a look at it directly if you want to. It's a 65816 CPU, a real one, Western Design Center, and it's a 128K memory chip. That's all. Any other questions? How much time is left?
Will there be a port for the past C64?
I heard that Jerry Ellsworth is working on it. Yes. I mean, the PAL DTV is already on the way. I've heard that the design has been pretty much finalized, so I'm pretty confident that Jerry will put some time into it. And well, if she won't do it, we'll do it. And, yeah. I can't tell when it's going to be released. Like I said, I can't promise anything that somebody else said.
Other benchmarks.
First of all, I don't really like this term emulation. Because it is not emulating. If you emulate something, then you write a program on a computer that already exists. You write a program that calculates how the other machine would have behaved if this program were to run. This is implementing the actual hardware. So you might want to call it emulated because it is new hardware running old software, but it is not one processor emulating another. So we tried to look for a new term for this, and the best term that we found is we are cloning the hardware. So you're right that just implementing existing machines is well kind of senseless if you already have the original machines. If you have this board and have all the machines in one, then it's already a nice thing to have it all in one, to have it on a VGA monitor, to be able to use a real PC keyboard instead of some old keyboard that has seen so much coffee and everything that it hardly works anymore. So one sense definitely is to have a brand new machine, a machine that is still serviceable in the 21st century. and that still runs your software. There are no benchmarks, but if you are speaking of benchmarks like I want to compare it to my P4 or whatever, then this computer is not what you want to look for. It's really, it will never compete with any high-speed PC, neither price-wise nor performance-wise. The front-side bus that is on this computer is clocked at a maximum of 133 megahertz. We are clocking it at 100 megahertz because at 133 we had a few problems. We didn't really get the SD-RAM working at 133, so we agreed to slightly above 100. And with that performance, you will never be able to beat a PC or PowerPC, Mac, or whatever you prefer. This machine will never run any of your favorite massive multiplayer games or whatever. It's a geek machine. It's something to learn on. It's something that is Windows free. And yeah, it's more educational rather than doing something that you want to use in your everyday life.
In the 80s, there was the golden age of computers. Nowadays there is more pieces, less of unique computers made by few people. Do you see one as a possibility to bring back this age and have lots of newly invented home computers?
It would be great if C1 could do that, yes, but personally I would see the C1 as a little bit too expensive to play such a role. It is, I would say it would have to be something like a €99 product to become something that revolutionizes the computer market again. I fear that this golden age of the 80s is really over, and you won't be able to change anything on it with the C1. Personally, I see the C1 as the first of its kind reconfigurable hardware of a completely different idea that implements hardware in a different way, not have this dogma of a PC must have a processor, it must have a graphics card and everything. It's well, a design study, something that could mark a new future for alternative hardware, yes. And, I mean, I have already started using this technology, this FPGA technology, the reconfigurability in a commercial product. I mean, the seminar shall be about FPGAs, so let me tell you a little bit about the Caprism Mark IV. It is using an FPGA out of the same group of FPGAs. It's a 1K30, so the size is the same as the smaller FPGA of the C1. The trick on the Caprism Mark IV is, again, this FPGA is brain dead when you switch the machine on. And the only thing that really works is the PCI bridge. So the computer can see the card, but the FPGA that is behind the PCI bridge is brain dead. What the driver software first does is it loads a core into this FPGA. So you have a piece of the hardware inside of your drivers. So whenever somebody is reporting an error to me and it is a hardware failure, then I can go back into the development system, fix this error, put this new core into the driver, publish the driver on the internet, and then somebody has done a hardware upgrade through the internet. The card will never have to be returned again. And this is something that, as far as I know, hasn't been done before. It is really using the FPGA technology to the max. Many other hardware designers that I've been speaking to, they said, well, I do not like FPGAs because they lose their contents if you switch them off. And this is a great disadvantage of everything that they say. I say it's a huge advantage because it's SRAM based. It doesn't wear out if you reconfigure it so and so often. I mean, your memory also doesn't wear out if you overwrite it so and so often. So it's not a drawback. It's a chance for the hardware. It's a chance for this FPGA technology to really take over, to have a piece of huge technology. And I think I'm going to continue using this technique because, first of all, it's a lot cheaper than CPLDs, and it's so much more flexible. You can use this hardware for things that you really haven't been thinking before. I mean, there's one guy here in the audience. He's going to use the capacitor for something completely different. Neither a floppy controller nor something SID or I/O-like. He's going to do something completely different with it, just because it is a reconfigurable FPGA on it, and it has some nice I/O ports to the outside. It has some memory connected to it. It's just so flexible. I mean, the commercial product has these core functionalities, but you can use it way beyond that. And okay, we got to cut it off here. Maybe one final question.
The complexity of the architecture input is limited by the FPGA, by the current models. Okay, can you give an example of how far we could take this product? Would be an architecture that just about fits one that is probably not going to work model, this model of FPGA.
This model of FPGA has 100,000 gates for the bigger ones, and for the bigger one, 30,000 gates for the smaller one. This is pretty much completely used if you are implementing something complex like the Commodore 64. So anything more complex will have to, for example, we'll have to outsource the CPU onto the CPU part. That's why we've done that. And since the CPU takes about a third of the whole FPGA, you can still do a lot after outsourcing this. And it's already been pushed pretty much to the limit. These FPGAs were state of the art when the development of the C1 has started. Until now, we've seen 2 new generations of FPGAs. And these 2 new generations it is the same as with CPUs. It's the same as with memory. Every 18 months, the capacity doubles. And I'm really excited about seeing new FPGAs, seeing something that really grows as fast as CPU performance. So, like I said, I see the C1 as the first of its kind of hardware that will probably mark a new, a milestone, reconfigurable hardware. And you've seen the first one. Well, that's it.